forward. Stat A, 8.1.2, sampling distribution. Sampling distribution of sample proportions. Day 2. So basically what we're talking about here is that we are taking a bunch of samples of P of, remember, we want our parameter, as a reminder, is P, which is the proportion of the population that are successes. And as I kind of did yesterday, like this, the population will change within each problem, and that what we're categorizing as a success. It's what we are trying to figure out. What is the binary thing that are male, that are going to want to come back another year, that are diagnosed, or whatever the thing is. And our statistic is P hat, which is the sample proportion that were successes. Once again, how we deem a success varies. So we are trying to figure out what proportion of the population of interest is we look like. What do all BPS students look like? What, for whatever variable or whatever is that we are, the binary piece that we are trying to investigate. Okay? P hat is equal to X over N, where X is the number of sample successes, and N is the sample size. What we've learned from here is that if certain conditions / assumptions are met, then the sampling distribution of sample proportions is approximately normal. And not only that, but the mean of the sampling, and we note it by saying the mean of the sampling distribution of the mean of the sampling distribution sample proportions, I just say mean of P hat, I use that as a subscript, is equal to P, the true proportion, whatever the actual portion is. On average, I should expect to get what the true population proportion is. And the standard deviation of the sampling distribution is the square root, and it's a big square root, square root of P1 minus P over N, where this is inside of here. So this is very important here. This is the mean and standard deviation of that distribution. However, again, I said if certain conditions and assumptions are met. So the question then lies, what are the assumptions and conditions? There are 3 assumptions / conditions that must be met for this to be true. And we kind of already talked about these in a sense. Now, for our purposes in here, I'm going to try to use, there's many ways to say it, and it's the same thing. the Desmos part is going to use sin. And this is one way of doing it. Sin. So the first one, S, stands for that the sample is random. We want a random sample. Okay? The sample is random. The second thing that we have is that it is independence. / we have less than 10% of the population sampled. Now, this middle piece right here about the less than 10% of the population being sampled confuses a lot of people. Basically, what happens is that in the real world, you are sampling from a finite population. So there's a limit to how many people there are. There's not an infinite number of students. We have like 500 students, or we have 800 students, or we have 200, whatever it is. There's a finite number of the population. When you take a sample, you do not want to sample more than, come on, we got to focus in terms of here what's going on with the computers and stuff, please. Stop playing your games or whatever it is. You need to focus. When you sample, you don't get the same person twice. So what happens is that if you sample more than 10% of the population, what ends up happening is that they're no longer independent. Because you'll know what the probability is. That once you have, because technically every single time you select one person, the probability of a success is now changed. When you select one individual and that person says, yeah, yes, or they say no, your total probability in the theoretical sense changes. But it's so small that it's insignificant. However, once we've crossed 10%, the math doesn't work out. All right? A lot of people won't even do this one right here or in here. And the last one is that we have a normality check. Okay. Now, for sample proportions, the normality check, because when we get to Friday, the normality check will change. When we get to sample means, the normality check changes. And so this in here, it's called the success and failures condition, which we've done before. And if you recall, the success and failures condition says that n times p must be at least 10, and n times 1 minus p must also be at least 10. So this is what we've done. We've actually checked this. Remember, this was in our last examination, our last unit, that is it normal? And we kind of did binary, and inside the bins, we checked independence inside there, or we did randomization. The only thing that's kind of new here is this like 10% piece, and then we checked this piece right here. Now, if all this is true, basically what happens is that we're saying that if I were to take a sampling, like if I were doing a bunch of p-hats, and you've seen this graph inside your Desmos, basically what's happening here is if I were to graph a bunch of p-hats, I know I'm overdoing it in regards to it, but I'm just going to do it this once. That when I graph all of the sample proportions, we call this the sampling distribution of the sample proportion. Now, the theoretical sampling distribution is the result of every possible sample of size n from the population. And I'm not going to go into it too much, but this is a really very important thing if you're really going to be studying statistics. Understanding what the theoretical sampling what the theoretical sampling distribution is. Basically, let's say this. We'll keep it kind of simple. Okay. Let's say, well, somewhat simple. Let's say there's only 10 students. Okay. And I'm going to sample 5 students. Okay. So the population is 10, and I'm going to sample 5 students. The sampling distribution, the theoretical sampling distribution, is what would be the results, what are the responses from all possible sizes of 5 from the 10. So, in other words, let's say 1, 2, 3, 4. I can say, it's actually 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. There's 12 people in here. So, how many different ways can I sample 5 students from 12? And what would your answers be? For what would your p-hat be? So, for example, 1, 2, 3, 4, 5. I sample these 5 people. That's one of the possibilities. And I record how many yeses or no, and I record the p-hat from these 5. Then I do 1, 2, 3, 4, 5. That's a new sample. That's a different sample. And I record that p-hat. And then 1, 2, 3, 4, 5. This over here, that's a new sample. 1, 2, 3, 4, 5. A new sample. 1, 2, 3, 4, 5. A new sample. 1, 2, 3, 4, 5. A new. Now, as you can probably see, if I were to, the mathematical number of how many possibilities there are is gigantic. So how many different ways can I take a sample of 5 from these 12 people? All right. Well, actually, we do have an answer for that. TI. Calculating for. And math, prob, combination, 12, choose 5. There are 792 different ways. And it doesn't sound, yeah, it's like, wait a minute, there was only 12 people. How are there 792 combinations of selecting 5 people? And I hope you kind of see it, because I just started with the same 4, and then I did, there's 1 sample, 2 sample, 3 sample, 4 samples, 5, 6, 7, and so forth. And then I can now choose these 3, and then start here, and then go 1, 2, 3, 4, 5, and we got all these samples. And it adds up. If I were to take every single possible way of sampling 5 of you from in here, there are 792 different ways. Now, if I were to take all of those p-hats from all 792 p-hats, sample proportions from all of the responses of sample size of 5, and I graph them, they would look approximately normal. All right? Now, however, condition 3 would probably fail. This condition right here would probably fail. It might actually look a little skewed. It would probably be a little bit smaller. So this last condition would fail in the example here of 12, from the population of 12 students. It wouldn't be independent because we're sampling 5 is more than 10% of 12. So it fails those 2 conditions. So in this example that I'm saying, it would not be approximately normal. However, let's say that I go from all of the school. Okay, from the entirety of the school. And then I sampled, let's say, 40 students from the entire school. Now we're talking. And then all conditions will actually be there. And let's say that there are 500 students in the school. Okay, 5. So if I do second math, or math NCR, and I say there's 500 students, and I select the samples I select 30 students, okay? I do a sample size of 30. That's how many possibilities there are. That is 1 followed by 48 zeros. That's like a gazillion, like a trillion, 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 trillion. different ways of doing it. So if I were to physically try it now, this is why we technically in the real world, we don't use we don't graph the theoretical sampling distribution, because there are 1 times 10 to the 48 possible samples. Can you imagine trying to graph that many dots? Even a computer would take a year to try to do that one. But that's how many different ones. And if we did that, all the conditions would hold, and it would be approximately normal. All right, so let's do an example. 22% of high school students skip at least 1 class a week. We randomly select 80 RBA high school students. A, describe the sampling distribution. Okay. Now, what I'm asking here, the sampling distribution should be approximately normal. All right. So we're going to check our conditions. We're going to check our conditions. So we're going to start off with sin. So is this sample random? Check. Is this independent? Is there independence, which means there is less than 10% sampled? Huh? Yes, 80 is less than 10%. I guess. Let's say there's more. Let's say there's 1,000 RBA high school students. I know there isn't. 80 is less than 10% of all students. And what about our normality check? Well, N times P is 80 times 0.22, which gives me 17.6. N times 1 minus P is 80 times 0.78, which is 62.4. Both of these are at least 10. So check, check, and check. All 3 conditions are met. So that means that the distribution is approximately normal. Okay, so let me go on to the next line. So X follows a normal distribution. X is approximately normal. Okay. I don't want to actually use that. So, so this is going to be approximately normal because all these conditions met. Okay, and the mean is equal to P. Well, what is P in this problem? What is P? What percent is success? 22%. So P is 0.22. So that's the mean. The mean is 0.22. And the standard deviation is the square root of P1 minus P over N, which would be the square root of 0.22 times 0.78 over 80. So if I go to my calculator, second square root 0.22 times 0.78 divided by 80, my standard deviation is 0.046. 0.046. So normal with a mean of 0.22 and a standard deviation of 0.046. There we go. Now, we're back to last unit. Everything that we did last unit, what you had on your examination, the next questions are just doing that. Now that I have the mean and standard deviation, the only thing I need to do is now we're going to ask a question. And these are now, what we've done has led us back to Unit 7. Question B. Where is it? What is the probability that at least 20% of students skip this week? So what's the chance that at least 20 students will skip at least one class this week? Okay? That's the question. So now, again, this is the same thing. So we have our mean, we have our normal model. The mean right here, we just found out mean is 0.22. And, sorry, I want to, and I said, here's 0.20 right there, right? And at least means we're going to shade above. This is where I said the exam happens. So you have to do, your last step is what you did in the last unit. Everything we learned in your last unit is the last step. And to now do this problem, I do a normal CDF. The lower boundary is 0.20, comma, 9999, comma, 0.22, comma, standard deviation 0.046. Now, sorry, and I meant of 80 sampled. I forgot that one. So it's 20% of 80 samples. So if I sampled 80 students, what's this? What if I sampled 80? What's the chance that at least 20% of them are going to skip? That they'll say I skipped a class this week. That's the question. And I go to my calculator. Second vars 3, second vars 2, clear, quit, second vars 2, 0.20, 9999, 0.22, 0.046, paste. 0.668. There's about a 67% chance that if I sampled 80 students, if I randomly select 80 students and I asked them, how did you skip a class this week? There is about a 67% chance that at least 20 of them will say, yeah, I skipped a class this week. The difference between a probability and a proportion can be very tricky. So now let's go back in here. So the key takeaways over here, I kind of summarized this down in here on the next slide. So slide 9 is summarizing what we just said in our notes. What we just learned. If you want to know the next slide, slide 10, if you're wondering why that at least 10 number is there, why there needs to be at least 10 successes and failures, this next slide helps explain that a little bit more in detail. So if you want to investigate, I told you, why is it greater than or equal to 10? Where does that 10 come from? This slide right here will help you answer that. And then we have 11, or slide 12, which is once again talking about the sampling distribution versus a sample. And now you have some questions that you're going to do on your own. Let me unlock this. We have on board for your work from home. Your homework or your work. Basically slide 13 and onward is your homework. Okay? Is the actual work. Slide 13 is, do you understand the vocabulary between a sample distribution and a sampling distribution? A sample distribution is what one single sample looks like. A sampling distribution, of course, is what the distribution looks like with a bunch of samples. Then you're going to confirm. We have basically two problems. I've just given you two problems, two scenarios. The first problem is this one right here. in regards to checking the assumptions and conditions for approximately normal. You'll do it again and check it for approximately normal, and then you have questions based on it. You'll check that it's approximately normal, and then you have some questions on it. What is the mean? What is the standard deviation? And then you have 2 problems to do. Very much like the notes that we did in the practice we did. That's what I have for you.